All right, so I'm going to pick up where the second video left off and talk about loops again. Now, we had that one really kind of awful diagram. We had the idea that a loop of wire, if we put our thumb in the direction of the current and we wrap our fingers around, we see that this comes out that end, around the back, and in again. And that creates a magnetic field that is very similar to a bar magnet. Now I want to do that in a more effective perspective, and that is to look at the face of the loop. And so if I have current traveling around the loop in this direction, right, then if I put my thumb in the direction of the current and I grab a hold of the loop, right, my hand is on the outside of the loop pointing toward the back, and to grab it I've got to wrap my fingers around up on the inside. That applies to everywhere on the loop, just like if you're driving a car, right, driving the steering wheel. My thumb points in the direction of I, my hand points on the outside, wraps around, and comes back through the inside, all the way around, okay? So what that does is on the outside of the loop, I have magnetic field lines that are pointing into the board. And then I'm going to wrap around the back and I'm going to come out through the inside. And what you get is you get a intense magnetic field on the center and relatively less around the outside. And if I was doing this carefully, I'd have the same number of X's and dots. And I'm pretty sure that I don't. Anyway, so that shows the arrows coming out the front side. So the North Pole is out here in the front and going back in, back around and in to the back side, and behind the board is where I would find the South Pole. So what happens is that a loop creates a magnetic field that depends on I and is strong inside the loop. Okay, so that's where that concept finishes up. All right, now what if we do more loops, right? If I can get a good magnetic field with one loop, what if I go around 2 or 3 or 100 times and do a bunch of loops, right? Then each loop creates a magnetic field and they add up together and create a very, very strong field on the inside of the loop. And if we do that, it's called a solenoid. So let's talk about a solenoid. All right, so if I have an empty tube, right, that I'm going to wrap my wire around, right? And so I'm coming up the front and I'm going around, and then I come around again, and around again, and around again, right? And I create a large number of loops. Okay, so I'm wrapping it around that tube. And so this one's on the front side and that one goes around the back side. And if I have my current going in this direction, the magnetic field created by the first loop is going to add to the one from the second loop and the third loop and the fourth loop, etc. And I'm going to create a magnetic field, right? And if I want to figure out the direction of the magnetic field, I want to grab it with my right hand. So here's my loop on the front, right? On the front, I'm going on the outside and into the hole and coming back around. So on the outside at the front, I'm going out and I'm going to wrap into the hole. So my magnetic field line goes around the outside and into the hole, and then it comes out again and continues. Okay, and this one goes in, across, and that's right. I'm switching my arrows. In over here, in over there, which means it goes that way and that way. Yeah. Okay. So grabbing this wire, I wrap around the front side of the solenoid into the opening, and then my fingertips come out on the inside of the tube. And so where it comes out is my north pole. Where it goes in is my south pole. And that's a solenoid. And the magnetic field strength of the solenoid is equal to mu zero, which is a constant that would be given at the top of the test. N is the number of turns. Right, the number of loops, because remember we said we get a certain amount of magnetic field for every single loop. So you got to know how many loops are there. Times the current divided by the length. So L is the length of the solenoid. So L is from the first loop to the last loop. That's what my L is. Which means if I take this same coil with the same number of turns and I squash it up short, this is a stretched out slinky. If I make it a short slinky, then it'll be a stronger magnet, because the smaller I make L, the bigger I make my magnetic field, because I get more magnetism scrunched into a smaller space. Okay, so what's a solenoid good for? A solenoid is good for an electromagnet. And they're used frequently in switching circuits. So when I turn the electricity on, it's a magnet. When I turn the electricity off, it's not. And so I can, for example, have a door latch like the ones in the dorms, that when the metal plate touches, then electricity flows, and it's a magnet and it's stuck, okay? And it's stay closed. And then if I push the button, it turns off the electricity. Now it's not a magnet and you can open the door. Your door locks in your car are solenoids. Your starter in your car is a solenoid. So while you're trying to turn the engine over, that electromagnet is acting to move you into one circuit to start the car versus a different circuit to run the motor. Okay, so solenoids are useful in a lot of places where you want a switchable magnet. Okay, so our solenoid is another application that you would need to be able to sketch a diagram for and explain how it works. Why does it become a magnet when the current flows, but not when it doesn't? All right. I want to stop here, and I'm going to do the next application on the next video rather than try to stuff it into the last few minutes here. So see you on the next video.